Every optimization problem asks the same question. What is the best you can do? The biggest box, the cheapest can, the farthest throw. Calculus answers all of them with one idea, the derivative. Let's see how it works. Let's look at an example where derivatives help us optimize, folding a flat sheet into a box. You have a 20 by 20 centimeter sheet. Cut a square of side x from each corner, fold up the sides, and you get an open box. How big should the cut be to hold the most? The base is 20 minus 2x on each side, and the height is x. So the volume is x times 20 minus 2x squared. Next, expand it and then differentiate. Setting the derivative to 0 and simplifying gives 3x squared minus 40x plus 100 equals 0. After solving the equation, x is 10, or 10 by 3. 10 would make the box vanish, so the winner is x equals 10 by 3, about 3.3 centimeters, giving a maximum volume near 593 cubic centimeters. Next, let's flip the question and use derivatives to minimize instead of maximize. A can must hold 355 milliliters, a standard soda. What shape uses the least metal? Its surface area is 2 pi r squared for the top and bottom, plus 2 pi r h for the side. Using the fixed volume to replace h, the area becomes 2 pi r squared, plus 2 times v by r. If we make it too tall or too short, it wastes costly material. To minimize, differentiate the area with respect to the radius, equate it to 0, and find r. The derivative is 4 pi r minus 2v over r squared. On setting it to 0, r cubed equals v over 2 pi. Plugging in the volume gives a radius near 3.8 centimeters. And here is the elegant part, the height comes out exactly twice the radius. The most efficient can is as tall as it is wide, using about 278 square centimeters of metal. Let's apply derivatives to concepts of physics. When a projectile is fired, its trajectory and how far it travels depends on the angle of launch and the initial speed. Given the speed v, shoot too flat, and it hits the ground early. Too steep, and it goes up but not out. Question is, what angle throws it the farthest? The range equals v squared over g, times the sine of 2 theta. Speed and gravity are fixed, so the only thing we control is the angle theta. That means we differentiate with respect to theta. The derivative is proportional to the cosine of 2 theta. It is 0 when 2 theta equals 90 degrees, so theta is 45 degrees. Hence, if the angle of launch is 45 degrees, the range is maximized on Earth or any other planet. Watch the 45-degree shot. It clears both the flat and the steep attempts, landing the farthest, about 40.8 meters. Still not convinced? Let's fire 5 more angles at random. Every one of them lands short of the yellow line. 45 degrees keeps its crown. And the range curve confirms it, rising to a single peak exactly at 45 degrees. Our last example hides a secret. Here is a cost curve. It could be money, error, or energy. We just want its lowest point. Let the ball roll. Where the curve is steep, the slope is large. As it flattens, the slope shrinks. It stops exactly where the slope, the derivative, is 0. The algebra agrees. 2x minus 6 equals 0 gives x equals 3. But now look back. The box, the can, the projectile. Every single one ended the same way. Set the derivative to 0 and solve. That is all optimization is. The derivative measures slope, and the best answer lives where the slope goes flat. One idea, for problems, endless uses. So the next time you need the most, the least, the fastest, or the cheapest, remember, take the derivative and set it to 0. Thanks for watching.